Hi, welcome to your lesson on 12.3 on analyzing geometric sequences in series. We just spent some time talking about arithmetic sequences in series in the previous lesson. A geometric sequence or series is a little bit different. The same idea though, we're going to create a sequence of numbers and then we can take the sum of those terms, which becomes a series. But for an arithmetic sequence, we constantly added something. For a geometric sequence, we're going to be multiplying or dividing. So basically, we can take a look at the ratio of consecutive terms, and so the ratio of consecutive terms has to be constant. All right, now just like last time, we took the we took the difference between the second term minus the first, and this one we'll take the ratio of second over first. It'll be kind of akin to what we did before. All right, that ratio has to be constant, and so we call that constant or common ratio R. All right, so the constant ratio between consecutive terms is the geometric sequences we're denoted as R. And finally, a geometric series says if you add up all the terms of a geometric sequence, you create a geometric series. Okay, pretty straightforward. Again, same exact lesson as last time, but instead of adding to get to the next term, now we're going to be multiplying. All right, so let's take a look. First, we want to tell whether or not this sequence is geometric. So we have to take the ratio of A2 to A1. So negative 4 over 1 becomes negative 4. All right, 16 over negative 4 becomes negative 4. 64 over 16 becomes negative 4. And 256 over negative 64 is negative 4. So since this is now negative 4, and every single one of them is negative 4, this is a geometric sequence. All right? Now, if you already looked down below, then you probably already saw this. This is not geometric, but I want you to verify that. So take just a second and tell me if you can figure out why this is not a geometric sequence. All right, so again, you have to check to make sure that the ratio of consecutive terms is consistent. It has to be constant. So if I do 128 over 512, okay, that comes out to 0.25. Okay, 64 over 128, well, that comes out to 0.5. And then 8 over 64 comes out to 0.125. In any case, these are not the same. So since they all don't match, this is not a geometric sequence. All right? So the general rule for geometric sequence then says the nth term of a geometric sequence with the first term of a sub 1, commonality, right? We talked about this being the first term. And now the common ratio is R. So last time it was the common difference, which was D. Now we're talking about the common ratio R. Becomes a sub n equals a sub 1 times r to the n minus 1. All right, so let's take a look here. Go ahead and try one of these examples. Let's write a rule for the nth term and then give the 10th term in the sequence. All right, so what we have to do first is we have to find out that geometric ratio. Okay, first of all, we have to find that common ratio r. And so we're going to do negative 324 divided by 972. And negative 324 divided by 972 comes out to negative 1/3. All right. The first term in the sequence is given. This is 972. So I got a little ahead of myself. So this becomes negative 324 over 972, and that comes out to negative 1/3. So my constant ratio, my common ratio is now negative 1/3. So using the pattern then, a sub n becomes the first term, which in our case is 972 times negative 1/3 to the n minus 1 power. And again, this is negative 1/3. Okay? Now, we can't distribute or do anything funky with that like we had to simplify last lesson, so we're just going to leave it like that. So then the 10th term of this thing becomes the first term, 972, times negative 1/3, and we're going to raise that to the n minus 1 power. So since I want the 10th power, this is going to, or the 10th term, this is going to be to the 9th power, because it's 10 minus 1. Okay? Now, plug all that into your graphing calculator, and then you're going to get a decimal, and then just use the math, change it to a fraction option, and it'll change it back to negative 4 out of 81 for you. All right? Let's take a look at example number 3 here. So in taking a look at example number 3, it says write a rule given a term and a common ratio. Very similar to what we did last time. We're going to give you a term, we're going to give you the ratio, see if you can figure out the rest. So in our case, we know that our common ratio is 3. All right, we're giving you the third term of the sequence is negative 18. So a sub 3 is negative 18. That becomes a sub 1, which we don't know, times our common ratio of 3, raised to the n minus 1 power. Well, since this is the third term, this becomes 3 minus 1. All right, so 3 minus 1 is 2. This becomes 3 squared, which is 9. So divide both sides by 9, and you get negative 2. So that says that my initial term, my first term, is negative 2. So then plugging everything back in, this is negative 2 times r to the n minus 1. But once again, we said before that r is given as 3. So this is 2 times 3 to the n minus 1 power. Now, this might look somewhat familiar to you because as we talked about in chapter 7 on exponential growth and decay, this was negative 2 times 3 to the x minus 1. So this should say that the initial value is negative, so that means it's going to work downwards. And since this number is greater than 1, this is going to be exponential growth. So it should look like an exponential growth graph that's down below the x-axis. Okay, let's see if we get that. Okay, my initial value, a sub 1. A sub 1 is negative 2. And to get the next term, we multiply by 3. So this is negative 6. This is negative 18. Our next term is negative 54. And you might need a calculator for the last one, but I'll tell you it's negative 162. So when I graph that, x is 1, y is negative 2. That's like right under the x-axis. When x is 2, y is negative 6, which is still right in there somewhere. That's probably more like 10, so it still should be a little bit higher. At 3, we should be at negative 18, which is down there. At 4, we should be at negative 54. These are counting by 20s. There's 20, 40, 60, so probably right in there somewhere. And then at 5, we should be at negative 162, 20, 40, 60, 80, 1, 20, 40, 60, so probably right in there. And you can see my graph is going to kind of have this feel to it right here, which that sure as heck looks like an exponential growth graph with initial value that's negative. Okay? All right. So why don't you try the 2 checkpoint problems at the top of the next page. Let's see what we can come up with here, okay? All right, so if I want to write a rule for the nth term of the geometric sequence, and then we have to find a sub n. Okay, so first of all, we got to do 28 divided by 14, and that tells me that it's 2. So my constant ratio becomes 2. So a sub n is equal to the initial value a sub 1 times r to the n minus 1 power. Okay, we know my common ratio is 2. My initial value is given as 14, and so a sub n is going to be equal to 14 times 2 to the n power, or 2 to the n minus 1. Okay, so if I want to find a sub 9, that becomes 14 times 2 to the 9 minus 1 power, or the 8th. Okay, plug that into your calculator. You should end up getting 3,584. All right, for the next one, now we give you the common ratio, and we give you one of the terms in the sequencer. So this is 324 is equal to the initial value a1, which we don't know. We know the common ratio is negative 3. We're going to raise that to the n minus 1 power. Well, if this is the 5th, then this becomes 5 minus 1, which is 4. Okay? Now, negative 3 to the 4th power becomes 81, so I'm going to divide both sides by 81. And I tell you then that a1 is going to be equal to positive 4. All right, and so now we get a sub n equals 4 times negative 3, raise it to the n minus 1 power. So if I want a sub 9, that becomes 4 times negative 3 to the 8th power, because 9 minus 1 is 8. Plug all that into your graphing calculator. You should come up with 26,244. All right? Okay, so this is that systems of equation stuff that we did in the last section. Now we have a couple of points. We have a couple of data values, if you will, and you can use that to make 2 equations with 2 unknowns. We do not know the initial value. We do not know the common ratio, but we're going to plug in all the stuff we do know. We have a sub 2, the second term in the sequence is 10. And so now we have 10 is equal to a sub 1, which we don't know, times r to the 2 minus 1, because this is the second term, so 2 minus 1 is simply 1. So that's r to the first power. Okay? In the second one, a sub 7 is negative 320, and that equals a sub 1 times r to the 7 minus 1, which is 6. So the first equation, I want to solve that for a1. So if I divide both sides by r, I get a sub 1 is equal to 10 divided by r. And now I'm just going to make a simple substitution. I'm going to replace a sub 1 with 10 over r in the second equation. So negative 320 is equal to a sub 1, which I know is 10 over r, times r to the 6th. Now this is r to the first power on the bottom. This is the same thing as r to the 6th on the top. So really you have r to the 6th over r to the 1st, which as you guys know is r to the 5th power. Okay? And so this simply becomes 10r to the 5th. All right? Now, to solve for r, we have to divide both sides by 10. All right? And so I get r to the 5th power is equal to negative 32. Now I take the 5th root of both sides, and I get r is equal to negative 2. Once I know r is negative 2, I'm going to go ahead and plug it back into this first equation. So I get 10 equals a sub 1 times r to the first power, which is negative 2. Divide both sides by negative 2, and you get a sub 1 is equal to negative 5. All right? Now that I know that a sub 1 is equal to negative 5, I can write my equation. So this was negative 5. And up here, r was equal to negative 2, I think was what we came up with. All right, so it's initial value, a sub 1, times r, my common ratio, which is negative 2, raised to the n minus 1 power. So there's my rule. Okay, checkpoint, top of the next page. Go ahead and try that one for me. All right, so now I have the 6th term, so 28 is equal to my initial value times r, which I don't know, to the 6 minus 1 power. So 28 is equal to a sub 1 times r to the 5th. And the second one, I have 224 is equal to a sub 1 times r to the 3 minus 1, which is 2. So 224 equals a sub 1 times r to the 2nd. All right, now, doesn't matter which one we do. I'm going to just pick this one here. R squared times a sub 1 is equal to 224, and so if I want to solve that for a sub 1, so I can do a substitution, divide both sides by r squared, and a sub 1 is equal to 224 over r squared. So now I'm going to take that, and I'm going to plug it into that first equation, all right, and that first equation now says 28 is equal to a sub 1, which is 224 over r squared, times r to the 5th. Well, as we said before, this is r to the 5th over r squared, which is r cubed. So I get 28 is equal to 224 times r cubed. Divide both sides by 224. And I get 1/8. So r cubed is equal to 1/8. Now I take the cube root of both sides, and I get r is equal to 1/2. I know that's kind of messy down there because I'm running out of board space. But you find out that r is equal to 1/2. Okay? We still don't have the initial value, so we're going to plug 1/2 into one of these equations. It doesn't matter which one. I'll just choose this one because it seems the easiest. All right? And so I'm going to move this a little bit over here to the left and see if I can squeeze it in over here. 224 is equal to a sub 1 times 1/2 squared, because again, this is r squared. So 1/2 squared is a 4th. To get rid of a 4th, we multiply both sides by 4. And I get a sub 1 is equal to 896. All right? So then a sub n is equal to 896 times 1/2. Raise that to the n minus 1 power. Okay? To find the 9th term of the sequence, we do 896, 1/2 to the 9 minus 1, which is 8. All right? And I end up getting 3.5, which is the same thing as 7 over 2. All right? All right, to finish the lesson then, let's talk a little bit about the sum of a finite geometric series. And this has a really cool practical application that we can talk about in the next lesson. But let's focus on this part first. Let's talk about the sum of a finite geometric sequence, or series rather. All right, so finite means that it stops, and so we're going to go up to the nth term. The summation of the terms for the first n terms becomes a sub 1, and again, for a geometric series, okay, again, different than arithmetic, this becomes a sub 1 times 1 minus r to the n over 1 minus r. Okay? So I know this seems kind of cumbersome, but that's just something that you'll have to remember. In this case, then, it says, all right, look, find the sum of the geometric series. As we said before, for any geometric series, this is a sub 1 times r to the n minus 1. Well, instead of n's, now it's just i's. Okay? So my initial value right here is 3. Now, you can certainly plug in 1 for this. This becomes 3 times 4 to the 1 take away 1. Well, 1 take away 1 is 0, and so you get 4 to the 0, which is now just 1. So 3 times 1 is 3. So we can get it that way. And then my common ratio there is 4. Okay? So since I know that the initial value is 3, this becomes a sub 1, or 3, times 1 minus r to the 13th power, which is 4 to the 13th, over 1 minus 4. Now, 1 minus 4 to the 13th, well, 4 to the 13th is a pretty good sized number, so 1 minus that's going to be pretty big, and then 1 minus 4 is going to be negative 3. So you have a very large number being divided by a negative 3, okay? So you end up getting something positive here. All told, you just plug all that into your calculator, and you end up getting 67,108,863. All right? So, checkpoint at the bottom of the page, you guys try it. We'll be right back with a solution. All right, a sub 1 is equal to 7, because that's this number here. My constant ratio, my common ratio is negative 5, because that's that number there. And so to find the summation of the first 11 terms, that becomes the initial value, a sub 1, which is 7. I want to multiply that by 1 minus the rate, or the common ratio, which is negative 5. And I want to raise that to the 11th power, because I want the first 11 terms, over 1 minus negative 5. Well, as you know, 1 minus a minus turns into plus. So on the bottom, this is really a 6. But I don't really have the ability to do negative 5 to the 11th power, at least not in my head. So I'm just going to plug all of this into my calculator. And what I end up with is 56,996,147.